Hello and welcome to the Spatial Integrated Systems virtual booth. My name is Rick Simon. I also go by Simo for my flying days with the Navy. My background is that I spent 31 years in the Navy, first enlisted, then at the Naval Academy, next as a surface warfare officer on a cruiser, and then as a naval flight officer in A-6 intruders and command of an EA-6B Prowler Squadron. I finished my time in the Navy in Virginia Beach at NetWarcom, standing up the Charnet Warrior experiments, and as the director for ForceNet for net-centric warfare. The project I want to talk with you about today is the Autonomous Deployment and Retrieval System, also known as ADRS. The company that this project is contracted with is Spatial Integrated Systems, also known as SIS. SIS was founded in 1997, and as of 1 January, just 2 weeks ago, we were acquired by Huntington Ingalls Industries. All employees were laterally transferred from SIS to Huntington, so the competencies and key personnel are still the same. We have more than 14 years of experience in robotics, and some of the key personnel include software and hardware engineers, computer scientists, retired military officers as program managers, a retired scientist from the NASA Jet Propulsion Lab, Dr. Terry Huntsberger, who helped develop the Mars rover autonomy. We are located in Virginia Beach, Virginia. Current contracts include unmanned surface vehicle autonomy work for the U.S. Coast Guard, executing a maritime domain awareness demonstration in Hawaii, ONR swarm work, and OSD SCO work with the CMOP program, which has now transitioned to the U.S. Marine Corps as the Long Range Unmanned Surface Vessel Program, also known as LRUSV. Additionally, we have ongoing unmanned groundwork with the U.S. Army at TARDEC, the Tank Automotive Research Development and Engineering Center in Michigan. The challenge of this project is to build a system that will allow small USVs to be autonomously deployed and retrieved from an autonomous mothership, another USV. This will allow those small USVs to be transported to operational areas autonomously and then deployed for missions and reused repeatedly while the mothership is on station. Currently, we are targeting a 10 to 12 meter mothership similar to the current LRUSV prototype. Additionally, we plan to operate in sea states up to 4, with small USVs weighing up to 150 pounds. The design of the system, however, allows it to be scalable. In other words, we can enlarge this system for carrying and deploying larger USVs. The ADRS system is truly aimed at being a force multiplier for the Navy and Marine Corps. ADRS increases operational flexibility and the probability of mission success where one USV can become many, allowing swarming and multi-USV cooperative missions. It goes without saying that working in high sea state conditions can be both challenging and dangerous, and deployment and recovery of unmanned systems in high sea states is not only challenging, but it is also currently requiring a significant amount of human physical interaction. To be able to do this work autonomously would significantly enhance unmanned system capabilities, and the design we have created allows for ADRS to be flexible, expeditionary, and scalable to other military unmanned vessels. The system as designed will enable safe and autonomous deployment and retrieval of small to very small unmanned vehicles in contested environments from autonomous host USV platforms, otherwise known as motherships. It will enable redeployment and reuse of those small USVs for additional missions, with the ability to recharge or refuel the small USVs and to download any data collected by them during a mission. The mechanical system pictured below has 3 major pieces to it: a latching mechanism that engages the nose of the small USV to lock it aboard, a cradle or funnel that captures the small USV and then dampens out the sea state motion, and a rack that transfers the small USV from and to the water behind the mothership. The software portion of ADRS embraces a precision positioning system using real-time kinematic GPS and advanced autonomous behaviors. The behaviors include undocking from the mothership for mission deployment. Upon completion of its mission, a rendezvous behavior is used to bring the mothership and the small USV together. Once the rendezvous is complete, then a lineup for recovery behavior takes over to position the small USV astern of the mothership. And finally, A recovery behavior is executed to allow the small USV to be captured by the mothership and transferred aboard. Final design has been completed and a technical design package has been developed and sent to a number of manufacturers to bid on the mechanical portion. We expect to start building in the next few weeks. Completion of the build should be accomplished by June. Software is expected to be validated by the end of August. Initial integration and testing with a government USV are expected to be accomplished in September. Simulation and on-water testing will continue in a relevant environment through November, and then integration to a government USV for testing and demonstration in an operational environment will commence in January and complete with a demonstration by July 2022. Key features and benefits of ADRS include removing humans from a dangerous and physically challenging job, and instead enabling autonomy to deploy and recover small USVs from a mothership USV, all while allowing the human operator to monitor the procedure from a command center. This not only increases safety for humans by removing them from the actual physical handling work, but it will also save lives by removing humans from combat environments. Again, the key features of ADRS include scalable. Design allows for growth to enable larger USVs to be carried and deployed from the mothership. Flexible and expeditionary. The system can be transferred from mothership to mothership. And fully autonomous. Humans will monitor and command, but not actually be physically involved. Next steps for transition to the fleet include building ADRS, the mechanical system, and the precision positioning system by this June. Finish developing behaviors by August. Complete initial testing and demonstration by November. Move ADRS to a USV for testing in an operational environment in January. Currently, we are on schedule to meet the U.S. Marine Corps LRUSV Program of Record requirements. We will also be available for U.S. Navy large and medium USV programs of record. Our primary transition advocate is NAVSEA as our sponsor for this project, and our secondary transition advocate is Marine Corps Systems Command and the LRUSV program. Additional opportunities are available in both government and commercial applications, and they include inspection of oil platforms, bridges, underwater tunnels, vessels, and underwater structures, bottom surveying, search and rescue operations following such events such as a hurricane, and fish finding operations. Our business model targets building near-term production models, either for sale to a prime integrator or to the government as GFE. And our business pitch for this technology is that the U.S. Marine Corps and the U.S. Navy require USVs with the ability to autonomously launch and recover other USVs and potentially UUVs, so they can be refueled, recharged, and redeployed for additional missions and as a force multiplier. ADRS will enable this ability. We intend to meet the Marine Corps Systems Command schedule, where the system is fully qualified and can be inserted into a program of record such as the Long Range Unmanned Surface Vessel, LRUSV, and will also be ready for fielding on U.S. Navy USV programs. How to reach us. Our phone numbers and email addresses remain the same for now as shown on this slide. I appreciate the chance to tell you about the Autonomous Deployment and Retrieval System, ADRS. I'll be happy to answer anyone's questions. Thank you for taking the time to visit our virtual booth.